Okay, let's look at some examples using cylindrical coordinates. In this first problem, we'll be using polar coordinates actually. So in this problem, a rod rotates in a horizontal plane. That's how we can get away with polar coordinates. And collar B slides down this pipe. Let's so kind of in this direction. We have a relationship for theta and a relationship for r. So let's further look at these. Let's completely characterize r and the rates and accelerations of r, because we need to find the velocity and acceleration at t equals 1. So r is 100 t squared. So at 1, r of 1 equals 100 millimeters. Okay, and then r dot equals 200t, and then r dot of 1 is going to equal 200 millimeters per second. And then r double dot just simply is 200 constant. So r double dot of 1 is also constant, 200 millimeters per second squared. Okay, let's do the same for theta. So theta equals t cubed. So theta of 1 is 1 radian. And then theta dot equals 3t squared. So theta dot of 1 equals 3 radians per second. And then theta double dot equals 6t, and theta double dot of 1 equals 6 radians per second squared. And this is why these sorts of problems are nice to do, because it's so easy then just to use a cookbook approach to solving. For velocity is r dot u of r plus r theta dot u of theta, unit vector in the theta direction. So this is, so our v at 1 is, just take our values up here and we plug them in. So we're looking at, say, r dot is 200 and r is 100 here, and theta dot is 3. So we end up with, and so we end up with 200 u sub r plus 300 in the theta direction, unit vector in theta direction. Okay, moving on to acceleration, we have this relationship, and just plugging in the values here, r double dot is 200 meters per second squared minus r of 100 times our angular velocity squared, 3 squared. That is our u sub r, and then we have 100 times the angular acceleration of 6 plus 2 times the radial velocity of 200 times the angular velocity of 3, and that is in the theta direction. And that produces this final result in millimeters per second squared. We should probably put units up here in millimeters per second. And it is trivial to find our magnitude of velocity and our magnitude of acceleration, as this is 361 millimeters and this is 1930 millimeters by just taking the square of the components and the square root of the sum of the square of the components. Here, you could also find an angle based on those components. Maybe that angle is delta, and we could say that angle is say 56 degrees here, and the angle down below is 68.7 degrees, just based on the x and y component, with the hypotenuse being the magnitude. So that is basically one type of problem that we use this cylindrical coordinates for. Essentially, you're given r theta, and either you're given directly the derivatives of these, or you can easily calculate them from a simple relationship like we did here. Sometimes, though, you have a situation where you need to define r or theta in terms of r or theta. And it's a little more complicated problem, but it's still doable. So in this next problem, we have a searchlight here, this blue thing, and it casts a light on the wall, a spot on the wall, which we can connect with a position vector from, say, here to there as position r. And let's use this as a perpendicular distance to the wall, which is 100 meters away. And then we have theta here, an angle between that is theta, and the searchlight is moving with an angular velocity of 4 rads per second. So let's find the acceleration and velocity when theta equals 45 degrees. So this is a good problem to use polar coordinates on. The only one of the issues, though, is that we really don't have a relationship for r. But we have a lot of geometry listed here, and we can come up with a relationship for r in terms of theta. So we can see that r really equals the magnitude of r equals, actually, let me write it like this: 100 meters over r equals the cosine of theta. So therefore, r in terms of theta is 100 over cosine of theta. And let's not deal with this in the denominator. We'll put 100 secant of theta. You, of course, could leave it in the denominator and just work with it like that, but I'm going to go with 100 secant of theta. Well, so now we have everything we need for theta. So we have theta, and then theta at 45 degrees. Well, we have theta equal to 45 degrees. Let's put it that way. That's where we're going to work from. We have a theta dot, which is given as a constant value of 4 rads per second. I should write here that this is constant. So it's swiping back and forth with a constant angular, which means that what? Theta double dot equals 0. So that simplifies that. But with r, we have to actually solve for our rate equations. So let's see, r equals 100 secant of theta. Therefore, r of 45 degrees equals 100 secant of 45 degrees is 141.4. Okay, r dot equals 100 times the derivative of secant, which is the secant of theta tangent of theta. But we've got to use the chain rule, d theta dt, or theta dot. So at 45 degrees, this is, let's see here. We're looking at 100 times, so that's this times this, which is given as 45, or 4 rads per second, times the secant of 45 times the tangent of 45. So it's 565.7 meters per second, and this is meters up here, actually. And let's give ourselves a lot of room for our double dot, because notice we have 1, 2, 3 parts to that when we use the product rule. So we'll have 100 times. So let's do the secant first. Derivative secant is secant theta, tangent theta, and then we'll have a theta dot there for the chain rule. And then of course we've got to tack on tangent of theta unchanged and theta dot. So that's our first term. The second time we'll take the derivative of tangent of theta. So secant of theta is unchanged, and then the derivative of the respective time of tangent of theta is tangent squared theta, theta dot, and then the other theta dot remains unchanged. Wait a second, that's a mistake. The derivative of the tangent of theta is the secant squared theta. Okay, and then finally, let's look at the theta dot. So we'll have the secant of theta remains unchanged, the tangent remains unchanged, and then theta dot is just theta double dot. Okay, there we go. So now it's just a plug and chug situation where for theta we put in 45 degrees, and for our theta dot and theta double dot we put in the values. Well, theta double dots are going to be 0, so this is going to kill this. And for the theta dots we just stick in the 4 rads per second. So my theta dots, I have one in each of these. So that's theta dot squared, so that's 4 squared is 16. I can pull that out with the 100 for 1600 and then stick in 45 with what's remaining for the angles here. And the end result is 67 and 6,788.2 meters per second squared. All right, so now we've got R dot, R dot, and R double dot at 45 degrees. We also have theta and theta dot and theta double dot, which just can plug and chug these into our relationships for velocity and acceleration. So here we are with our relationships, and I will just grab values from above so these are the values for the particular coefficients, and we can simplify this to just 565.7 in the R direction plus, strangely enough, 565.7 in the theta direction. And for acceleration, again, it is plug and chuggable. So R double dot is 6788.2, and then R theta is 141.4 times theta dot squared, and then for R is 141.4.0, so this is going to go to 0, plus 2 times R dot is 565.4 or 565.7 times 4. And then here's our results, multiplying those out. And we can, of course, use these components, square them, add them together, and take square root to find our magnitude of velocity and magnitude of our acceleration.